Greetings everyone. On the request of our viewer, I have decided to create a tutorial on the stress assessment using machine learning, but instead of ECG, I am going to use a PPG signal. If you want to know the difference between ECG and PPG, this graph is very explainable to understand the difference. The black graph is basically the PPG signal and the red graph is basically the ECG signal. You can see that there is a lag between the peaks of both ECG and PPG. But for this stress diagnosis, PPG is enough because ECG require particular clinical setup. ECG is costly. It requires particular expertise to use the ECG, and it is also time taking. On the other hand, PPG is very low cost. It didn't require any time. It is actually can be used in your wristwatch. You can buy a simple sensor to even use the ECG. The sensor I have used is this Groove air clip heart rate sensor. This sensor is quite low price and this provide actually data in the form of digital wave. So if we want to see the data this sensor can provide, the data provided by the sensor is in that form. The peak actually show the R wave, like this peak is digitized in this graph. So the idea is to get the distance between these two peaks, which is quite easy when you are using a digital signal like the signal which is in the form of 0 1. The signal has just 0 1 format. But if you have the signal in the form of other value, like there might be some values between 0 and 1, look like this is some sort of analog signal, then you have to clean the signal, and then once you got the peak, you have to find the interval between these peaks. If you are using ECG, then you have to find the interval between these two peaks, which are actually called as R to R peak. If you are using PPG, you have to use these you have to find the distance between these two peaks. Okay, so this will provide us R to R interval or peak to peak interval, that is peak to peak interval. So let me explain the data further. The data is taken from 27 subjects, and here is the explanation of how we collect the data. And the way we introduce test is using a mobile app, which is actually color word stroke test. The subject has to select the color, and you can read this paper, actually machine learning based real time diagnosis of mental stress using photoplethysmography. You can email me to get this paper, and or you can even purchase that. So it will be help you to understand the data collection process and how we introduce this stress among the individual using a mobile app. So for example, in the mobile app the word green is written in red, but the subject has to mark it red. So this makes it confusing because the subject is reading the word green but the color is red, so the subject has to make the color red. And there are different levels for this game, and we are collecting the data for 5 minutes, both for when the subject is playing this game and when the subject is not playing this game. There are further pre-processing steps, such as first we compute the distance between peak to peak values, which I have already told you. Then we remove the outliers, and then we apply the Outlier filter to smoothen the data. This will also remove the noise from the data. The main area of this work is basically feature extraction. We have used a lot of features, that is time domain feature and frequency domain feature, and also the nonlinear feature. Let me explain some of the time domain feature. You are aware of the root mean square difference, standard deviation or difference in peak to peak interval. That you have the peak to peak interval and you have to calculate the standard deviation. This is a very simple thing. And the other thing is NNI-50, that number of successive peak to peak interval pairs that differ more than 50 milliseconds. For example, if you have this graph, you have to find the number of interval which have this different as more than 50 milliseconds. Let's say if the difference is more than 50 milliseconds and the length difference is also more than 50 milliseconds, so you have to see how many of these interval have the difference of 50 milliseconds. Similarly, we have the normalized peak successive PP interval pair, and we divide the NNI 50 by total NNI, that how many total interval pairs, and then we the same thing is NNI 20 and PNNI 20. The NNI 20 is similar to the NNI 50 except that number of successive PP interval pairs that differ more than 20 milliseconds. Then we have average heart rate, standard deviation heart rate, mean, maximum, and absolute difference. Also, we are aware of, if you are from signal processing background, you might know that what is the energy of the signal. Then we have also frequency domain pair, that the power of low frequency, very low frequency, high frequency, and the total power, their ratio, peak value in very low frequency, high frequency, relative power of low frequency. There are a lot of features which we are going to extract from this data. And there are also the nonlinear features such as standard deviation in point care plot, which is perpendicular to the line of identity. You can see point care plot from here. This is basically the point care plot. Actually, we are getting this ST1 value and SG2 value, and further we are going to take their ratio. There are other trend fluctuation analysis and entropies such as sample entropy. You can calculate other entropies such as approximate entropy, Shannon entropy. There are a lot of other things. We have also the fractal dimension. Fractal dimension is basically, if you are going to, let me explain fractal dimension from this data, from the image basically. This is the fractal dimension, that there is a pattern in every small breakdown. If you break the signal into small chunk, there is still a pattern exists which is going to replicate. For example, this steric pattern is repeating again and again. So if you increase the length, the pattern repeats itself more and more. So this is about a fractal dimension, and there are different ways to calculate that. So you can read all of these things and in this paper, which is actually machine learning based real-time diagnosis of mental stress using photoplethysmography. In my approach, actually I have connected this sensor with the Arduino, and then Arduino is connected with the Python, and the goal is to, as the data came into Arduino, the data is transferred to Python via serial port, and we are passing the data in Python to a machine learning classifier. So this is the ultimate goal of the research. So let's start to the coding part. The first thing I have to do is to install the entropy library, which will give me access to some entropy based function, so I can calculate the entropy of different data. Meanwhile, the entropy function is going to install. We can view what next we can done. We have imported some of the libraries, which are pandas, numpy, matplotlib, statistical library, entropy library. The entropy library has been installed, and we are now going to import these libraries. After that, we have to read the file. You can also get this data from this Kaggle. I will share the link in the description. Let me view the data. The first column is basically subject ID. The second column is the label. You don't have to understand the rest of the column because they have no meaning. Actually, the data is in the form of rows. So this whole row is basically a single subject. This whole row is basically the RR interval of the single subject. The next row is the RR interval of the second subject. The third row is the RR interval of the third subject. You can see that there are a lot of NaN, because sometimes the data has been collected for more than 5 minutes, and sometimes the game is completed before the 5 minutes. And you can also see that there is some sort of redundancy, such as 630 has been repeated twice. And here you can see that there are basically sometimes the same value is repeated twice, because it is some sort of related to sampling frequency of the sensor, because the sampling frequency of the sensor is very low. The next thing I have to do is to get the labels and data separate. So I am going to remove the first two columns. Which are the two? Now I have these columns. I am going to transpose these, and let me show how my data now look like. Now each of the column represent a subject. I have 54 column. The reason why 54 column, because I have total 27 subject. So 27 multiplied by 2 is actually 54. Why I am multiplying by 2? Because each subject has to go one time with normal, because each subject has to go with stress test and without stress test. So that's why I have multiplied with 2. So there are two columns for each subject. The 0 column and then the 27th column is belong to subject 1. The first column and the 28th column belong to second subject. The second column and the 29th column belongs to third subject. Basically, things like that. Then we have the label, and after that I am going to drop all the rows which are totally null. In my case, all the rows aren't totally null. There are some of the values, and let's see, this is how the data we got. The shape of this data is 337 into 54. 54 are the basically shows the subject in trials, and 337 is basically the length of signal for each subject. Then I am going to plot the data of one subject, that is subject 1, which is 0 to 1 and 27 to 28. Basically the last value is excluded, so we have 0 and 27. So this is the stress baseline and stress data, and now we are going to remove the outlier. Actually you can use different techniques to remove the outliers. I am going to remove this by choosing all the values which are greater than 1000 and all the values which are lesser than 600. I can even reduce this value to basically 500 also. So this is my data after I remove the outliers. So this is how it look like. The next thing, I have to apply the Escole filter, which will further smoothen the data. And now if I view this data, it look like it removed the tiny noises, because previously we had removed a lot of noise, but this time we have removed the very tiny noises, very small noises. Now I have to calculate the feature: mean, median, maximum variance, standard deviation, maximum, and the following. So the first feature I am going to calculate is the range, which is actually maximum minus minimum. Then we have root mean square, which is taking the square root, then taking the mean and the difference of the interval, and then taking the power. And then we are going to take the standard deviation of the difference of the signal, which is standard deviation of the difference of the signal. Similarly with the NNI50, we are going to calculate the NNI50, which I have shown you what is the meaning of NNI50. Actually NNI50 is the number of successive PP interval pair that differ more than 50 milliseconds. So first I am going to calculate the interval, and p.diff actually calculate the difference between the signal and the lag of its own signal. And I'm going to see that I'm going to choose all that which are greater than 50. Then I'm going to take the absolute and then take the sum. Similarly with the PNNI50, I'm going to divide this number with the total length of it. The same thing with the NNI100, and I'm going to calculate the average heart rate, minimum heart rate, maximum heart rate, energy, absolute sum of the difference. Sum of absolute difference is basically a measure of similarity between the signal and its lag signal. So these are the time domain feature I am going to use. Now next I am going to apply all of this function onto my data frame. For that I am going to use this aggregate formula. I'm also going to calculate mean, variance, median, maximum, minimum, and the custom defined function. So once I run this, it will show me the feature like this, that for this subject 0, for this subject first I have 683 mean, and the variance is 1425, median is 684, and for the same thing like the rest of the subject. Now I am going to extract the frequency domain feature. For that I am going to use SciPy library from Python, and I am going to call the packages. The shape of my data is 337, 54, and the length of data is 337. So the first thing is interpolating the data. The reason why I'm interpolating the data, because the sampling frequency of my data is not uniform throughout the process. So I am going to interpolate it to a sampling frequency of 4 hertz. So first I will take the cumulative sum, then I will apply the interrupt P1D formula from the SciPy interpolate, and then I am going to calculate the step size, which is actually inverse of sampling frequency, and then I am going to see that for what range I have to calculate these, and then I'm going to apply this function on this value. So now you can see that this is the interpreted data. Previously it is like ending at this point, and now it's been interpolated, and now it looks like more better one. So next thing, I have to get the frequency domain feature, which are actually power of very low frequency, total power, peak value. So first I have to find the low frequency, very low frequency, and high frequency. It should be high. So I am going to first get all the frequency between 0 to 0.4. Then for the low frequency, I have defined as 0.04 to 0.15. Then for high frequency, I have defined 0.15 to 0.4. Then I am going to calculate power in each band by integrating the spectral density. After that, I am going to sum these to get total power, so that I can find the NU relative power of low frequency. After that, the next thing I have to do is to calculate the peak of the next thing I have to calculate the most power in each band, which means that I have to calculate the peak value in the power band. What is the peak value in the high frequency, what is the peak value in the low frequency, and what is the peak value in the very low frequency. After that, I am going to calculate the relative power of low frequency band in normal units. And now I am going to append them all of these values in a list, and I'm going to convert this list into an array. So this is going to do that thing. Ignore this error. Now I am going to convert this data into the data frame, because I have this in array format. So these are the features in the frequency domain. Now I am going to combine the time features versus frequency features, and these are the feature I have got. I have got around 28 columns, which are 28 features, and the total number of subjects are basically 27 multiplied by 2, because I have taken data twice from each subject, one for without stress and one with stress. Next, I am going to do some statistical analysis. So I am starting from 0 to 27, that is 0 to length of feature divided by 2, that half of the subject, then the rest of half of the subject, because first half of the subjects are basically without stress and rest half of the subjects are with stress. So I am going to calculate the student t-test between stress and non-stress for all subjects. So this is what I will get. So you can see that the p-value for mean is 0.000123, which I believe is less than 0.015. Similarly, there are a lot of features, around 25 features out of 28 feature, I believe that, which have p-value less than 0.05. It means that out of 28 features I have calculated, 25 features show significant difference. Okay, the next thing, I am going to split this data into train, test, split, and I am going to apply classification. Before the classification, I will scale the data so that my data is being normalized, and after that I am going to apply the support vector machine classifier. So I am going to get around 0.82% accuracy for the support vector machine classifier. Next, I am going to see the predicted value, and now I am going to plot the classification report. You can see that my F1 score is also quite good, that 82%, and precision and recall are also very good. And the number of subjects in this test is 9 from normal class and 8 from stress class. This is the confusion matrix. You can read this confusion matrix, that what is true positive, what is true negative, what are their importance. Eventually, this confusion matrix is used to calculate this precision recall F1 score. So personally, I do not calculate the confusion matrix because I directly calculate this classification. One thing I can also use is to use logistic regression CV. What is logistic regression CV is like it provide me a very good score, that is 96%. I'm not sure how, but just ignore that. You can see that why we got that too much score. But when I am going to apply cross-val score, that is cross validation using sport vector machine classifier, and the CV, which is how many fold I have to split the data, and I have put it as 10, then I'm going to make 70, then I am going to achieve 72% accuracy. After that, I am going to call all the classifier, all the known classifiers, or the most famous classifier, and I am going to compare their performances. So I have used k-nearest neighbor, sport vector machine, decision tree classifier, random forest classifier, Gaussian naive Bayes classifier, quadratic discriminant analysis, AdaBoost. So there are a lot of classifiers that I am going to use, and I am going to create a pipeline. The first pipeline will do is that it will scale the data, and the next thing it will classify the data. So this is the purpose of pipeline, and I'm going to pass this pipeline to the cross-val score, and I have put this CV equal to 27. The goal is that during each splitting I want one stress case and one non-stress case into the test data. So let me read it from here. It will be more clear if we go to this paragraph. I believe we are using leave out classification method such that all subjects except one from each class are fed to the machine learning classifier, and the performance of classifier is tested on those two subjects. This process continues until classifier performance is tested on all pairs of the subject. So this is my ultimate goal. So I am going to call this, and you can see, okay, look like I have missed. You can see that I got around 81% accuracy using sport vector machine. Similarly, 81% accuracy using random forest. The accuracy with the Gaussian naive Bayes is 24%. With gradient boosting classifier is 68%. And here I am going to compare all of these accuracy. The highest accuracy I got is using sport vector machine and random forest. And the lowest accuracy I achieved is using quadratic QDA, that is quadratic discriminant analysis. In this paper, I have compared a lot of other things, that what is the impact of hypertuning, what is the impact of feature selection, and what is the impact of GA, which is actually genetic algorithm. There are a lot of things which you can read in this paper. And let me know if you have any question, and you will get the code and the data and the paper in the description.